Okie doke. So in this video, we're going to look at more advanced magnetism in terms of what we've seen in the previous video about basic magnetism. Now, one of the most important things is that we don't want to just talk about magnetic field lines anymore, because they actually have a specific name. So if we draw back in our situation from the end of the previous video, which was looking at magnetic field lines between, I'll call that one north, this one south, between these two magnets. And this, what we see here, these, what we have previously suggested are magnetic field lines, are actually what we call lines of flux. And they actually have their own measurement entirely. And we go by the unit Weber. Or Weber, depending how you want to say it, but it's pronounced Weber. And it's represented by the symbol Thi here. So a number of Webers is basically like a number of field lines. Even though it's just a representation, I wouldn't say that this had 4 Webers, because actually 4 Webers is actually quite a lot of Webers. But we wouldn't call this 4 Webers. It's just a representation of the field lines. But it numerically, it would be in Webers or Webers, however you want to say it, as long as you remember to pronounce it or write it correctly. I suppose that's the most important thing. So that's represented by a symbol Thi in an equation, and WB as a unit Webers. Now, these Webers, or flux lines that we call them, so flux lines, are effectively what's responsible for magnetic interactions. And there's an equation that effectively explains what puts this together with another term, which is called flux density, which is represented by the letter B in equations. Now, the letter B is the flux density of the amount of flux that you have in a certain area. So if I was to put a circle around this, effectively you've then got an area. And that area, A, is linked with these 3 factors like so. That B is equal to an amount of Webers per unit area. So where you have a certain amount of area, you have a certain amount of Webers per unit area. And this flux density has the unit of Tesla, or T. Now you might think this is an interesting unit, because this is effectively the same thing as the amount of Webers per meter squared. So this is the same unit effectively, and it's nice to see this unit coming out, because a lot of people hear of Tesla and Tesla coils. Well, this is Tesla. Teslas are a measure of flux density, i.e. the amount of flux lines you have per unit area, which is a nice simple explanation for what this is. So that's what flux is and flux density is. And normally we define flux density as the amount of flux per unit area, so the amount of flux per unit area, because we usually ask to define flux density. So it's the amount of flux per unit area. Well, we can go a step further now, and we can start to look at these situations with flux density involved. We're going to use, again, the same situation as before. We've got our 2 magnets, our north, our south, and our magnetic field lines. And now we have proper terminology for all of this, we can actually start to talk about it properly. Now we're going to put the wire back in. Remember, this wire exerted a force downwards. And we know that because we've got Fleming's left-hand rule, current going in, magnetic field. Oh, wait, I've done this the wrong way around, haven't I? So we've got the magnetic field going in that direction, current in that direction, and the motion up. So since I've already drawn this, I'm just going to change it to a spot because I don't want to redraw my drawing. So this time the current is coming out of the field. I'm just going to rotate my hand here. So I've got the current coming out of the field, my field lines in that direction, and my thumb is now pointing down. So that's correct. So what if we wanted to work out the actual force that was being affecting this current carrying wire? Well, there's an equation for that. And the equation is F is equal to BIL, where F is the force that is felt by the current carrying wire in that magnetic field. B, as we've already spoke about in the previous sheet, is the flux density of this magnetic field. So how dense these magnetic field lines are, which kind of nicely makes sense because the strength of this magnetic field is told by this flux. So the more flux density we've got, the greater the force is going to be, and we can see that quite nicely. And then we've got the current. That's the current running through this wire, in this case out of the page. And so the length is one that's a bit more difficult to show with this diagram, but it's the length of the wire in the magnetic field. Now what I'm going to do is I'm going to try to draw a three-dimensional picture on the side here to give you an idea of what that length represents. So if you were to imagine, here's my two bar magnets with the magnetic field passing between them. Well, the length of the wire is the length of the wire in that magnetic field. So here's your wire, here's the current running through it, and magnetic field. The length, this L up here, is the length of the wire in the magnetic field. That's a very important length, and usually it's quite nicely determined by the length of the magnets more often than not. So what we have here is a really nice equation to allow us to work out the force acting on this current carrying wire. And we can put this to use practically in lessons, because what we're hopefully going to do is set up a practical where we have a weighing scale underneath this. And what will happen, depending on which direction the current is flowing, this will either create an upwards force due to equal and opposite reaction on the magnet arms that are holding that in place, or it will push down as an equal and opposite force. And we'll talk more about those equal and opposite forces in lesson as a result of this force here. So in lesson, we're going to utilize this equation to help work out what, hopefully, the flux density is of this magnetic field.